Ever feel like math has its own secret language? Well, you're not wrong. It kind of does. And today, we're going to crack one of its most important codes, set theory. In just the next few minutes, you'll get the logic that powers everything from massive databases to, yeah, even your music playlists. So, let's dive in.
Okay, so you see these symbols, and they might look a little intimidating, right? Like some secret code. And in a way, they are, but they stand for really simple ideas about how we group things together. We're about to solve this puzzle, and you'll see just how straightforward it all is.
So, before we can start combining and comparing anything, we need to meet the main characters in our story. Let's define our players.
At the very heart of this is the set. A set is, well, it's just a group of things. That's it. These things, which we call elements, can be numbers, letters, names, you name it. The most important thing to remember is that each player, each element, has to be unique on that team. No duplicates.
For our first few examples, we're going to be working with these three sets. So we've got set A with the elements 1, 2, 3. Then there's set B, which has 3, 4, 5, 6. And finally, set C with 1, 3, 4, 6. Got them? Good. Keep these in mind as we head to our first operation.
All right, let's get to our first move. This is where we start looking at our different teams and finding out what they have in common. You know, the players that are on both rosters.
This is called the intersection, and it uses that symbol that looks kind of like an upside-down U. When you see this symbol, just think, what do these sets share? We're looking for the elements that are in both Team A and Team B at the exact same time.
So, let's try one out. Looking back at our set A and set B, which players are on both of those teams? What's their common ground?
And that's it, the number 3. It's the only element we can find in both set A and set B. So, the intersection is just the set containing 3. And hey, you've just solved your first set theory problem. See? Not so bad. Okay, so that's finding what's shared. But what if we want to do the opposite? What if we want to throw everyone from both teams together for one big all-star game?
For that, we use the union, which is that regular U symbol. This just means we're creating a brand new, bigger set with every single element from both of the original sets. But here's the key rule. You only list each element once. So even if a player is on both teams, they only get one spot on the all-star roster.
All right, let's go back to our teams, A and B. If we combined all of their players into one superset, what's that going to look like?
And there's our all-star team. 1, 2, 3, 4, 5, 6. We just took every element from A, every element from B, put them all together, and we were careful to only list our shared player, the number 3, just one time. Simple as that.
So far, our sets have just been kind of floating around in space. But to understand our next big idea, we have to actually define the boundaries of their world. And that boundary is called the universal set, usually shown as a capital U. Think of it as the complete list of all possible players that are available for this particular game. For any given problem, all our other little sets are just picking their teams from this one master list. Now, once we have a universe, we can talk about the complement. The complement of a set, which you see here with that little bar over the letter, is basically its opposite. It's every single element in the universe that isn't in our set. It's everyone who got left on the sidelines.
So let's check out a new scenario. Our entire universe of players is now just the numbers 1 through 5. That's everybody. And from that universe, set A has chosen its players, number 1 and number 5.
So the question is, who got left behind? Which elements from our universe are not on Team A?
Exactly. If the whole universe is 1, 2, 3, 4, 5, and Team A is just 1 and 5, then everybody else, 2, 3, and 4, makes up the complement of A.
Okay, now that we have our 3 main tools in our tool belt, intersection, union, and complement, we can start combining them to solve some much more interesting puzzles. This is where it gets fun.
Now, this might look complicated, but we just solve it one step at a time, like order of operations. First, as step 1 shows, we have to figure out that complement of B. Our universe is 1, 2, 3, 4, 5, and B is 2, 5. So everything not in B is 1, 3, 4. Okay, easy enough. Now for step 2, we just plug that result back in. The problem is now, what's the union of A and our new set 1, 3, 4? Well, we know A is 1, 5, so we just combine them, remembering not to repeat the number 1. And that gives us our final answer, 1, 3, 4, 5. See? By just breaking it down, the problem becomes way easier.
So we know how to do the calculations, but let's take a step back and think about why this all works and, what the limits are. This is where you really start to master these concepts.
This slide shows the beautiful logic of sets. Let's walk through it. Imagine set A has 2 players and set B has 3. Let's think about their intersection, or overlap. What's the most they could possibly have in common? Well, 2. That would happen if the entire smaller team was inside the bigger one. And the least they could overlap? 0, of course, if they shared no players at all. Now let's think about their union, their combined team. What's the largest it could possibly be? 5. That happens if they're 2 totally separate teams. And what's the smallest their combined team could be? 3. That happens if the team of 2 is already inside the team of 3, so when you combine them, you don't add any new players. Understanding these limits is the real key.
And this isn't just some niche corner of math. As the famous mathematician Paul Helmos said, set theory is the language in which modern mathematics is written. What you've learned here is a foundational building block for so many advanced topics.
And this logic, it's not just for mathematicians. Think about your music app. It has a set of songs you like. It also has a set of chill electronic music. When it finds the intersection of those 2 sets, boom, there's your perfect playlist. Set theory is the quiet, powerful logic running behind so much of our digital world. The next time you use an app, ask yourself, what sets are being combined right now to give me this experience? Thanks for watching.